So I should first of all thank the organizers for giving me this talk, opportunity to give this talk, and I should apologize to Frank for giving this talk on the computer.
You misunderstood my email.
Okay. So I'm going to talk about complexity aspects of constructible sheaves, and I want to structure my talk. So if I'm going to give a talk with a title like that, I should probably give some motivation, and I'll give some motivation, some of it I hope would be clear as I go along in the talk. So there will be some motivation. And then I will spend quite a bit of time on the background, which I also would like to say the qualitative part of the talk, which is going to be nothing new, but I'll try to recall some definitions, probably look at some structures in a different way than what you might be used to thinking about them. And then I'll mention some new results in one part, which is the quantitative or effective part. And finally, I would establish some connections with complexity theory. But I should make, for this part 4, I should make a couple of statements. So when I talk about complexity theory, I would always restrict the questions about our complexity classes to the Bloom-Schoop-Smale model. That's what I consider as my model of interest. And in particular, in this talk, it will be Bloom-Schoop-Smale model over the real numbers. That's the only kind of complexity classes I talk about. And I should also remark that, as Frank said, this theme of this semester is about applying geometric techniques to questions, answering questions to complexity theory. And there was a workshop a couple of weeks ago when a lot of interesting mathematics was presented. They're applying these mathematics to complexity questions. My goal here is somewhat more modest. In fact, I would like to look at questions that I'm interested in through some lens of developed by complexity people. And if there is some backwash back into complexity theory, that would be even fantastic. But for the moment, I'm more interested in this other direction. Okay. So I'll just go through the motivations quickly. So first of all, we'll see that constructible sheaves provide a more geometric language and kind of more expressive than the usual first-order logic, which we'll explain. It provides, in a certain sense, a topological generalization of Tarski-Seidenberg quantifier elimination theorem, which has been something that people have studied from complexity aspects for a long time. So it is interesting to study these quantitative questions in this more general setting. Something that I will not talk about much, but I should mention is that the theory of constructible sheaves, in the sense that I'm going to define, has applications in many other areas, including in pure mathematics, in D-module theory, or in algebraic theory of PDEs, and also nowadays in computational geometry and topology. And finally, I'm going to make some interesting, to me, extensions of the traditional Bloom-Schoop-Smale complexity classes, leading to questions or analogs of questions like the classical P versus NP type questions, which might in fact be easier to resolve a priori than the classical BSS ones. And in any case, quantitative study of sheaf cohomology in a more general setting of sheaves than the ones that I'm going to discuss here might be interesting, and it is interesting on its own right. Okay. So that's my spiel for giving this talk. So now let's start the background. Semi-algebraic sets, I really don't probably need to recall the definitions, but here they are. So semi-algebraic sets over real numbers are subsets of Rn, which you can define by Boolean formulas whose atoms are some finite number of polynomial equalities and inequalities of the form p equals 0 or p positive. Okay. Those are the semi-algebraic sets. And a semi-algebraic map, well, what is a map between semi-algebraic sets whose graph is a semi-algebraic set. Now, it follows just from staring at this definition that semi-algebraic sets are kind of robust category because they are closed under various operations, like any kind of finite set-theoretic operations, unions, intersections, as well as taking complements, taking Cartesian products, or more generally fiber products over polynomial maps. They are closed. And it also takes a second more, but it also follows from the definition, plus the fact that if you compose polynomials, then you get polynomials, that semi-algebraic sets are closed under taking inverse images of polynomial maps. You don't have to do any work to observe these. But here's a well-known but non-trivial fact that proved by Tarski in the 40s, that in fact not just the pullback under polynomial maps, but in fact the direct images of semi-algebraic sets under semi-algebraic maps are also semi-algebraic. Now, equivalently, Tarski was a logician, so his statement in the language of logic, which I'm not going to insist on too much, so I'm not going to explain what this means by defining the first-order theory of reals, but I will explain through a picture which will come later.
So
yes?
This theorem depends on the field being the real numbers, or?
No, this is for, so for most of the talk, you can assume that the underlying field is an arbitrary real closed field. But let's assume that this real closed field is a field of real numbers, real numbers.
So so this theorem, the general statement of the theorem is for a real closed field, this is true?
Yes, it is true.
And that's
also a version for algebraic closed.
Yeah. That's Lefschetz principle, but I know that GM would jump at this logic statement, so let's ignore this logic statement, okay? So, but you should have no problem with the first statement, which is equivalent, okay? All right, but I am going to make this next slide might look a little pedantic, but I want to restate Tarski-Seidenberg in this kind of slightly more pedantic way, because later on we are going to have some suggestive analogies. So let's forget about semi-algebraic sets. Let's just consider maps between sets. Let F be a map between two sets x and y. Then, just tautologically, there are some induced maps between the power set of x to the power set of y, which are defined by taking, so F inverse, F star is just the pullback, and F exists and F all are these maps. So they go from, so they go from in those directions.
I don't understand the third one.
The third one is you should think I'm looking, given a set A, I'm taking its complement, mapping, and taking its complement. So if you're thinking about universal quantifiers, eliminating a universal quantifier is...
So what's the easiest example where that's not the image?
Easiest example, yes.
Same.
So if you want to say what F exist A is, what is the relation with y, I put an existential quantifier. Well, this is the set of y such that there exists an x in x which maps to y.
Exists an x in A.
Exists an x in A. Right. And F all is the set of y such that there are all x in A. Okay. This is tautological. There's anything
all
fancy.
X in A intersect F inverse.
What?
All x in A intersect F inverse.
A intersect
F inverse of y.
F, but if...
Yeah.
Okay.
Anyways,
That's what he said.
for all x in A, f of x equals y. Yeah, sure. Something like that.
Yeah, something like that.
But it's clear, yeah.
There's nothing here. But these are in opposite directions, so you might be tempted to say that they are inverses, but they are not quite. But these maps are not inverses of each other, but they are somewhat inverses in the sense that they satisfy adjointness relation. So when I talk about adjoint, so I'm now thinking of these maps as functors. Don't be afraid of this word. I'm now thinking of these power sets as categories whose objects are the subsets of X. And it's a trivial category in the sense that I put an arrow between two subsets only if the one is included in the other. So that's a kind of trivial poset category. And and these are functors between those corresponding categories, and they are adjoint. And that's just a fancy, chic way of saying that, well, this is included in B if and only if A is included in F star B. Yes.
I don't understand the notation. What is that funny symbol in the middle? I mean.
Yeah. So this means that this functor is left adjoint to that functor.
Okay. And this middle
And
one
so
is left adjoint. Okay.
Yeah, that's the adjoint. And to say left adjoint means if you have two categories C and D, you have to. So this is left adjoint to that, means that for every object A in C and B in D, there is a kind of natural bijection between. So this bijection has to be taken, this home is in D. So there's a natural bijection between, and this home is in C. But again, this is all very trivial here in this, what am I doing here?
Yeah, that's fine. Yeah. That's what it is.
Okay, thanks.
So why don't you write the for all and there exists as subscripts?
Okay, if you want. But I cannot fix it right now. All right. So now, so arrow-theoretically then, Tarski-Seidenberg says that if you have now semi-algebraic set, and this is an important notation, I'll denote by S of X this set of semi-algebraic subsets of X. And if you have a polynomial map, then those arrows that I defined in the previous slide restricts not to the class of semi-algebraic subsets. Right? So it goes from F in these directions. And they carry semi-algebraic subsets to semi-algebraic subsets, and they satisfy the adjointness relation. That's Tarski-Seidenberg. But yet harder fact is true, which is more than Tarski-Seidenberg. And in order to state it, I need another definition, namely that of the notion of triviality of semi-algebraic maps. So we say that semi-algebraic, or you can think polynomial map between semi-algebraic set is semi-algebraically trivial if there exists a y point in the base and a semi-algebraic homeomorphism between X and this product of the, so X sub y is the fiber of y. So if there is a homeomorphism like this, but this homeomorphism should preserve the fiber. So it should be a fiber preserving homeomorphism. So another way of saying that is that this diagram here should commute, where P is the homeomorphism, F is the map, and P is the projection on Y. Okay, so that diagram commutes. So of course, not all semi-algebraic maps you can hope to be semi-algebraically trivial. By the way, if it is semi-algebraically trivial, then all the fibers, this follows from this definition because this map is fiber, this homeomorphism is fiber preserving, it follows that all the fibers are semi-algebraically homeomorphic. So of course, you cannot expect that all semi-algebraic maps are semi-algebraically trivial in this sense, but something almost this thing is true. So this is a theorem of Hart, which says that if an arbitrary semi-algebraic map may not be semi-algebraically trivial, but there exists a finite semi-algebraic partition of the base into locally closed semi-algebraic subsets, such that the map restricted to the inverse images of each one of these pieces of the base is semi-algebraically trivial. Okay, so here's a picture. It's not a very good picture, but suppose you have a projection map, which is polynomial map, from the green curve onto R2. So I'm thinking of this as a projecting from the green curve onto R2. And then there is a, so this is not semi-algebraically trivial, but there is a partition of the base of R2 into three pieces, which are locally closed semi-algebraic set, namely the complement of the curve, this open piece where the fibers are empty, in fact, then the curve minus that point, which is again a locally closed, and fibers are one point and that point. So that's the partition, and that's. I'm giving this in a sequence. We can think of the hard triviality theorem as a generalization of Tarski-Seidenberg. Why? Because Tarski-Seidenberg says that the projection, the image is semi-algebraic. So in particular, this image, this f of x, by heart must be a union, in fact, a disjoint union of some subcollection of the yi's. Because the fiber being empty or not, the hard partition is a finer partition. Well, even
demonstrating anything beyond the existence of Whitney stratifications? I mean, why doesn't it?
Whitney stratification is even stronger, so then I have to say harder, right? We are not saying anything about how the stratas fit together, right? So it's just so if you assume, so to prove Whitney stratification would be more than proving hard, because there is no condition on the tangent spaces, so there is no C infinity structure.
But it's true.
It is true. Say about Whitney conditions and things like that, but there's no Whitney conditions here. But in fact, that's from the complexity point of view, I should say that computing. So very soon we are going to be interested in not just the theorem, but how hard it is to and how many pieces you need. And in this case, this stratification is simpler than the Whitney stratification, because then the complexity of Whitney stratification is much worse because we have more conditions. But there is some drawback here of the hard theorem, that we are maintaining the homeomorphism type of fibers, but the homeomorphism type is a kind of difficult to quantify. It's undecidable really to check whether two fibers are homeomorphic. And also that the best complexity upper bound known for this induced partition is doubly exponential. So we come to kind of the formalism of constructible sheaves here. And the formalism of constructible sheaves seems to be just the right kind of compromise. Might agree or not, but I hope to convince you of this, between maintaining homeomorphism types of fibers and just Tarski-Seidenberg. So here we have to take a brief detour, and when I was preparing the talk, it's kind of a dilemma here, because of course for people who are familiar with the definition of sheaves, this will be nothing new, but people who are not familiar, it will go too quickly. But I hope at least to convey to the people who are not familiar the main geometric ideas, which you should be able to grasp. Okay, so let's take this little detour. In any case, it doesn't hurt to see the definition of sheaves one more time in your life for those people who. So let A be a fixed commutative ring, and for simplicity, we are going soon to take A to be a field of characteristic 0. Might as well take A to be rational numbers. I'll stick with A for a little bit, and then. So a pre-sheaf on a topological space of A-modules, by the way. So we're not talking about the complicated sheaves like OX modules or things like that, just constant. So it associates to every open in U, A module, and if A is a field, a vector space, F of U, and such that, and a restriction homomorphism for every pair opens V and U, we contain in U. And this restriction homomorphism, so for U, every time V is contained in U, there is homomorphism of the corresponding vector spaces, and it should satisfy the obvious conditions that you expect it to satisfy, namely R of U should be the identity. They should compose properly. So if W contains V U, then. And sometimes, so for probably just the next slide, I will. So by the way, these elements of S of F of U are also called sections, and that refers to the right picture in the first slide. If you think of the constant sheaves where all these modules are just one-dimensional vector spaces, then that corresponds sections, and for each section in f of u, we'll sometimes denote the restriction by to a subset V by S restricted to V. And so that's a definition of a pre-sheaf. And given a pre-sheaf, there is a more or less canonical way to make it into a sheaf. So sometimes we will get pre-sheafs that will sheafify into sheafs, but a pre-sheaf is a sheaf if it satisfies these two additional properties. That is, for every open U and an open covering Ui of U, if you have two sections that restrict to the same sections on each Ui, then these two sections of U better be equal. Maybe I said it with one of them equals 0, but that's equivalent. And this global property, namely that for such an open covering, if you have sections over each of the UIs which glue together properly, namely they restrict to the same sections or all pairwise intersection, then there indeed exists a global section which restrict to those SIs. So a fish sheaf would be a sheaf, it satisfies this. And then the stock, which I think of the left picture in the first slide. So a stock of a given pre-sheaf at a point x in x is defined to be the inductive limit over all opens containing x. In our case, we'll have sheaves which are, well, let's defer this for a moment. But unfortunately, we need something more. So if it was just sheaves, it would be simpler. But we need to go to the derived category. So here, the derived category of sheaves on X. So now the objects are not just, so the category, maybe I should say a few words about the category of ordinary sheaves. So the category of sheaves on a fixed topological space is an abelian category. So everything that you can do with vector spaces or A-modules, you can do with sheaves. So you have exact sequences, you have morphisms, you can take direct sums, tensor products of sheaves, and you get sheaves. But now we are going to go to a somewhat more nasty category, namely the derived category of sheaves on X. And this is the most difficult slide. If I go through this slide, then I'm home free. So here we can think of the objects of these are not just sheaves, but complex. Well, we first start with a category whose objects are complexes of sheaves. And whose morphisms are homotopy classes of morphisms of the complexes of sheaves. Now this category now becomes nasty, and well then you have to localize with respect to a class of arrows, which I don't want to say, such that complexes which are homotopic to 0 become isomorphic, and you get the derived category and sometimes the bounded derived category of complexes which are bounded on both sides.
I think you mean the complex is almost subject to 0.
Okay. Yeah.
To 0.
Each other becomes.
Now this is no longer an abelian category, which is not going to bother us too much in this talk, but it's what's called a triangulated category. It satisfies axioms that take several pages to state. But you have to replace exact sequences by distinguished triangles and so on and so on. But there's no point in going through this. But for our purposes, it will be okay to think of an object in the derived category as a complex of sheaves, even though you have to keep in mind that they're just representing something in the derived category. Now, if X is a point, then so there's a point, so an object in this derived category is represented by a derived category of just complex of A-modules. The sheaf is just, and in this case, this one is isomorphic in the derived category to the complex you obtain by just taking the cohomology of this complex. Wait, this is not true in what? It depends, but I'm taking A to be a field. Then it's okay. That's right. Depends on A is a field. And, or in other words, this thing here is, so that's a little bit So you have to read it as the direct sum of complexes. Each one of them is 0 in only one degree, namely Hn is non-zero only in degree n. And you take the direct. So that's. But this is not true in general. If x is not a point, you cannot think of taking the homology and representing it. If I have time, I'll show an example, but probably I won't have time. Okay, so we are now going to have operations on sheaves, and in your mind you should think of going back to this the operations about for semi-algebraic sets, namely pulling back and pushing forward. So if you have now even here they are just sheaves on x and y. Even if you start with sheaves x and y, and if it's a continuous map, then the inverse image is going to be a sheaf on x. And you don't need to go to the derived category here because this is a better functor. It's exact. I don't want to explain why, but as usual, think back again for semi-algebraic sets. Pulling back semi-algebraic set, get semi-algebraic set for free. Pushing forward is the more difficult thing. And here we have to take, in order to get full information, the derived direct image. So even if you start with a sheaf, if you push it forward, one considers here an object in the derived category of y. So here the object looks like a complex of sheaves. And since it's a complex of sheaves, we'll denote by Ri the higher derived images, the sheaf that you obtain by taking the homology, the ith homology of this complex, and that's a sheaf. So this Rf star is an object in the derived category. That's an ordinary sheaf.
How do you push forward a sheaf?
Well, R0 is just what you would expect, right? So you are given a sheaf here. You have a sheaf here. So what would be the associated for each open U in Y? Well, you take the F inverse of U, which is open in X, and you but that gives you just R0. But this is not an exact functor, so you get higher derived images. It's left exact, but not exact. So, but maybe we should just take a special case when.
To be exact, you need to be an open continuous map.
So the maps that we are going to consider all projections, but it will not be exact, even if it exists. So in the special case, if you take the constant sheaf on X, namely that sheaf that associates to every open the field A, then in this case, like I will describe what these higher direct images, you can think of it as associating to each open in U, complex A-modules where you take some kind of Claddy resolution of A restricted to F inverse U and apply the global section functor. So that's a humongous, going to be a big sheaf of complexes. But if you take a point in Y and you look at the stalk of the derived image at Y, then this is, after all, since it's a point, it's an object in the derived category just of A-modules. And in the category of A-modules, we know that any object in the derived category is isomorphic to taking its cohomology. So, in fact, this stalk here is going to, in the case when the sheaf is the constant sheaf upstairs, is just going to be the direct sum of the cohomology of the fiber over Y with coefficients in A. So the stalks are, in the case when this is a constant sheaf, has this purely, so this is the ordinary cohomology of the fiber. If you think of this being a map between semi-algebraic set, the stalks, and F is, let's say, a polynomial map, the stalk of the derived image at a point in Y is really isomorphic in the derived category of vector spaces or A-modules to the direct sum of the cohomology of the fibers. So now maybe I go back to something that's high school example. So whenever one talks about Tarski-Seidenberg, this example comes up, so I stick with the tradition. So if you have a formula like that over the reals, there exists x as x squared plus 2bx plus c is 0, then it is equivalent, and that's quantifier elimination for Jm, that you can eliminate. So that's a quantified statement in the first order theory of reals, and you can eliminate this quantifier to get an equivalent formula in this first order theory, discriminant non-negative. What does it mean to geometric formulation of this? Well, you define upstairs a variety in the XBC space defined by x squared plus 2 0. If you look at the projection from XBC to BC, and what you get is this picture. So the pi of V, I don't know whether it's visible. Pi of V is where the discriminant is non-zero. So so the projection is a semi-algebraic set, this closed semi-algebraic subset of R2, and its complement is this open part of R2. So the fact that the projection of this semi-algebraic set is semi-algebraic, the blue. Now, this is the sheaf-theoretic version. Well, you consider the constant sheaf upstairs. Well, the constant sheaf upstairs, well, you take the constant sheaf on R3, but we really want the constant sheaf on V. So you can think of restricting this constant sheaf to V, or more accurately, you just push forward the constant sheaf of over. So this is the what?
Which one was V, the open and the closed?
No, V is upstairs. So V is defined by this equation. X squared plus 2bx plus c. And then you project V, then you get the blue part under pi of c. V is a real variety in R3. So this sheaf here is whose stocks is constant on V. Stocks are equal to Q for points in V and 0 outside. And now you look at the derived direct image under this map pi, right? And so what about the stocks? Well, now it's even worse, but okay. So if you want to look at the stocks, then the stocks will depend on where you are in R2. So if you are here in U, which is outside the image, then the stock of the derived image is 0. If you are here, it is Q plus Q. Of course, I'm writing this. These are represented by, so they have degrees, right? So only in degree 0 there is something non-zero, and because the fibers have no cohomology. So it's Q plus Q. But if you are on the boundary here, on this locally closed, well in this case closed, you get, since there's a double point over the discriminant, then the stock is isomorphic to Q. So in this sense, just like in Hart, the fact that the derived image is, if you look at the stocks, it's giving you a final partition of the base. Okay, so I skipped this example. So this example was to show the.
So sorry,
yes.
Either is Q or 2Q. You don't keep the multiplicity.
We don't keep the multiplicity.
It's not kept.
No. It's constant. So as I said, the is just the ordinary cohomology of with coefficients in A's. So we just thought.
But the fiber should be non-reduced, so you should write it.
No, if you take some more complicated sheaves, okay. But here we are just taking sheaves with constant coefficients upstairs. So. Yeah, so it's much simpler sheaves than usual ones that algebraic geometers would study.
I'm sorry, I just have a question. So what did we gain looking at the high school example, by looking at sheaves? What do we gain?
Well, the Tarski-Seidenberg just tells you it's a partition into 2 parts, and here it's a partition into 3 parts. I call that a little gain.
Okay, but are they this? Do we obtain the boundary as well, or is this 3 new parts that are?
No, that's the boundary. But in a more complicated example, you get more complicated partition than.
Okay.
High school example, you can't expect. So Yeah, so this example that I'm going to skip because I did not get an anticipated question. So, namely that so the example was to show that the higher direct images themselves do not determine the object in the derived category. So if you take like the Hopf fibration, which is like this, and the trivial fibration, which is sphere, and you look at the higher, so I'm just going to skip this very quickly. So they give you the same direct image downstairs, even the same stalks, but they are not isomorphic in the derived category, because if you take the hypercohomology of 1, you should get the cohomology of S3, and here you should get cohomology of fiber. And by the way, for complex algebraic geometers, this kind of is sort of used as a counter example to this famous theorem of Deligne called the decomposition theorem, which apparently is not holding here, but it's okay because in fact this is not a complex algebraic map between non-singular hypersurface. I mean varieties. S3 is okay. Just an aside. Okay, so we have been talking about sheaves, but what about constructible sheaves? And this is the following definitions of Kashiwara and Shapira. So an object in the derived category, bounded derived category of X, is said to be constructible. Now X is now restricted to a locally closed semi-algebraic set. If it satisfies the following two conditions, and you have to keep the picture of the high school example in mind here, that there exists a finite partition of X into locally closed semi-algebraic sets, not necessarily Whitney or anything, just a finite position in locally closed semi-algebraic set, such that the cohomology of the sheaves are constant, are locally constant on elements of this partition. So that's in the case of the high school example, this is satisfied by this partition. You look at the, and you take this sheaf, so this is a constructible sheaf on R2, and on these three parts, the homology of all the homologies are locally constant. And we have some kind of finiteness of the stalks. So the cohomology groups should be finitely generated, and they should vanish outside some big, outside some. So we'll denote this category of constructible sheaves by this, and I'll forget about this notation in a second. I'll just call constructible sheaves on X the set of objects of this category as CS of X. That should be an analogy of S of X, which we are defined as the set of semi-algebraic subsets of X. So CS of X, objects which are constructible sheaves on X.
So just briefly, what extra flexibility is this buying you that's so precious to you?
Well, it gives you a better decomposition of the base for the moment. You'll see. You just take the Tarski-Seidenberg tells you whether
You just have two pieces.
two pieces where the fibers are empty or non-empty. It retains more information about the fibers, at least in this geometric example.
And it doesn't try to deal with
It doesn't try to deal with homeomorphism types.
So far, you could have passed all the way down to constructible functions and it'd still buy you this, but with sheaves.
No, constructible functions might. So you can obtain constructible functions by taking the Euler-Poincaré of the stalks, but then Euler-Poincaré. But this kind of generalized Euler-Poincaré could be 0 for non-empty fibers. In this example, yes. But imagine that you can have a circle.
It could be different.
Yes, yes.
Are you going to explain why you take one and not the other?
But so the constructible, the fibers here retain more information than just the Euler-Poincaré characteristic. Because, for instance, the Euler-Poincaré characteristic of the fiber is a circle would vanish.
I agree, that's true. But why do you want to keep that information?
That's a more philosophical question, to keep more information about fibers, which I think is kind of, if you are thinking of projection onto a set, image of a map, you should really understand how the fibers vary, not just empty or non-empty. The Euler-Poincaré would be a little better than being empty or non-empty. This is much more better. And if you take homeomorphism types, it will be even better.
case, if you just have a finite to one map, which
Yes,
is easier, then is it just the number of...
It's just a number. In that case, it will just, well, not quite, because you might have a finite to one map that looks like this. So it's not quite the number, because if you take the partition, even though the fiber is always 2 points, but the homology is not going to be locally constant. So, but more or less. Okay, so good constructible sheaves. So now, so that's one of the big theorems of the Kashiwara constructibility theorem. So you should think of this again as a kind of analog of Tarski-Seidenberg, which says that if you have a continuous semi-algebraic map and you have constructible sheaves F in CSX and G in constructible sheaf on Y, then the pullback, well, pullback of G is a constructible sheaf on X. The derived image of F is a constructible sheaf on Y. So the class of constructible sheaves have this kind of stability property that is closed, not just under these functors, it's also closed under taking all kinds of sheaf-theoretic direct sums, tensor products, internal homes, and things like that. Of course, the theorem of Kashiwara and Shapira was much more, and I'm not going to talk about these other operations, but in fact, the classic constructible sheaves closed under a wide range of sheaf-theoretic operations, namely those classical 6 operations.
One of these is a cousin of F for all, and another is a cousin of F exists.
This one, these two, well, this is with compact support, so let's forget about the shriek. So that's like F exists. F all does not have a, so you can try to create one using some kind of duality functor, but I don't want to go there.
If you did, it would be F shriek.
Yes.
F shriek is dual, F star dual.
That's right. So there is an adjunction on this category which goes F upper shriek left adjoint to F star might be, and then which is left adjoint to F up. Well, anyway, so I'm not going to write it. Okay, so that we should think of this as some kind of very sophisticated Tarski-Seidenberg. So that's the end of the qualitative background. I've not said anything. So now let's talk about quantitative. So let's go back to quantifier elimination. So this quantifier elimination has a really long history. It started with a non-elementary recursive algorithm of, well, recursive bound on Tarski's original algorithm for doing quantifier elimination. And then there was a kind of hiatus. Mind you, people are not looking at it. But then in the 70s, when this kind of problem became popular because of applications in robotics and stuff like that, Collins, but also it's usually attributed to Collins, but also Utrecht, gave a doubly exponential algorithm for performing quantifier elimination using a technique called cylindrical algebraic decomposition, which is a kind of very important technique for triangulating semi-algebraic sets. Now, there was again a hiatus, and there was a new ingredient called the critical point method, which was developed by Grigoriev and Vorobjov. And this gives a singly exponential algorithm, but let me state this statement in a kind of, because I'm short of time, in a succinct way, by introducing a notation. So for each n, I will denote by pi n, which forgets half the variables in Rn by projecting. So let's fix this notation pi n. So it was proved by Rennegar in 92 that the complexity, both quantitative and algorithmic of the functors, so remember this is, and maybe that's the reason why I put the exist and all in this superscript, n, which takes semi-algebraic sets, subsets of Rn to semi-algebraic sets of Rn over 2, is bounded singly exponentially. Maybe I should explain what this means. It means that if you are given a semi-algebraic subset of Rn defined by, in terms of, let's say, S polynomials of degree bounded at most by D, then the image of this here, by either of these functors, is going to be, you will be able to define the image in terms of number of polynomials and degrees which are bounded singly exponentially in N. And you can obtain this description here, going from here to here, by an algorithm which also has singly exponential complexity. Of course, their results are more precise, and then we made some more precise estimate later. But for the purposes of this talk, it's just the singly exponentially, the functor is singly exponential is what's important. Okay, so that's quantifier elimination, but we are going to talk about sheaves. So what can we say about the direct image functor? Well, this is the new statement that if you look at the direct image, the complexity is both quantitative and algorithmic is bounded singly exponentially. And here I really should explain what this statement means. So more precisely, if you start with a constructible sheaf on Rn, because we have this restriction of having compact support, you can get rid of this restriction by considering sheaves on some compact space, like on the sphere. But for the moment, let's take sheaves on the compact support. And suppose you have that there exists a semi-algebraic partition of Rn, which is subordinate to F, subordinate in the sense of the definition of constructible sheaf, defined by sign conditions on at most S polynomials of degree at most D, so on. So then there exists a semi-algebraic partition of Rn over 2, which is subordinate to the direct image sheaf, having complexity which is singly exponentially bounded. Might be slightly more precise, but that's the main thing that I want to convey. Moreover, there exists an algorithm to obtain this partition from the given partition with the same complexity. So we are going from partitions to partitions, which are partition subordinate to F to partition subordinate to F. And moreover, you can say something about the stalks, that this, if you knew something about the stalks upstairs, the homology of the stalks, then the homology of the stalks in the direct image again grows at most singly exponentially.
Maybe a question, how is these sheaves, the input sheaf, how is it given? So you
we are not
partition, and then on each piece of the partition?
No, we are not. The algorithmic statement is not about the input sheaf, but you are taking the partition. You are given only the partition, which you are totally subordinate to the.
Because you say also algorithmic, so it's also when you say algorithmic.
Well, so what I mean here is these three statements. So if you are given a semi-algebraic partition, which is subordinate to some sheaf, you can produce a partition which is subordinate to the.
But what do you need to know about the F itself?
Other than you need to, for these two statements, you don't need to know anything other than the partition which is subordinate.
You're given a partition.
It's just a partition.
Just a partition.
The F can be anything.
Yes. So I'm not saying.
Subordinate.
Yes. And I'm not saying that I'm able to compute the stalks.
Okay.
This is just a bound.
So I agree. Okay, good. So I'm
Yes.
confused about that.
I'm sorry, I'm still trying to see what you gain from this new reformulation. So, as an application of this theorem, would you get an easier proof of your real algebraic Toda theorem or something?
I'll come back to the Toda in a moment, but not an easier proof. Yes.
So, does subordinate to mean that f is constant on each part or locally constant?
Locally constant. Even if it's locally constant. So if it's constant, it's even better, but even if it's locally constant. So in fact, we have to reduce from the constant to the locally constant to constant. So I'm not going to be able to give a proof of this theorem, but I will indicate some of the ingredients that go into this, and one of the ingredients relates to your question. So meaning it follows kind of in a certain way my previous work with Kolya-Vorobjob which proves singly exponential bounds on the number of homotopy types of fibers definable maps. So maybe you can think of this as the case of the theorem with the sheaf upstairs, it's just the constant sheaf. And then singly exponential size covering by contractibles, and that relates to your question. So we have developed for some other purposes an algorithm which is singly exponential complexity that gives you covering of a given semi-algebraic set by locally closed semi-algebraic sets which are contractible. And so if you are given a subordinate partition with elements are just locally constant, but if you now cover it by contractibles, then they will become constant, but you pay a price. It goes singly, but singly exponential is so big that these kind of things don't matter. So there are some delicate thickening and shrinking arguments here when you are dealing with locally closed stuff. Some spectral sequence and some basic theorems of constructible sheaves, which goes into this proof, which is kind of long. So end of thing.
Do you appeal to the previous theorem about the, how to say, you mentioned some single exponential bound?
Yes.
You appeal to that.
Yeah. So it really uses all kind of machinery that has been developed for dealing with semi-algebraic sets. Okay, so now the complexity aspect of this, and might be we can get to Maurice's question at the very end. So let's recall, so the definition of Bloom-Schuff-Smale complexity classes, and I must apologize to one of the authors of this because I'm going to mangle this definition, but
he'll see you at the break.
Okay. So we have been. So of course, here in the Bloom-Schuff cells, a language is a sequence of subsets of Rmn. So I will introduce a notation. I'll call S to denote the category of sequences, where Mn is some non-negative function. And now we say that such a sequence is in PR in the BSS sense, if there exists a BSS machine which recognizes this sequence in polynomial many steps. Now, recall these maps I introduced right in the beginning, go from M to M over 2 in these directions. So you have sequences of those maps for each M. Now, this polynomial class has the nice property, which is reminiscent of the property of semi-algebraic set. It's a stable undertaking products, set-theoretic operations, but all of sequences here. And even pullbacks. So PR is closed under set-theoretic operation products and pullbacks. Why under pullbacks? Well, it's just maybe 10 seconds of thought that if you have sequence which is in polynomial time, pullback should be also in polynomial time. But what about the stability under these two other functors? And that brings us. So these functors here, and that's the reason I define this category of sequences, induce in a natural way, and now this becomes endofunctors because it goes from S to S. I'm only writing them in different directions to stress the adjointness. But so this one, okay. So they are still, they have this adjoint property. And we have the following obvious equality and inclusions. Namely that if you apply to the, so remember that the PR is a subset of sequences in S. So you apply pi star, you get back PR. It's closed under these pullbacks. But if you apply these two, then you certainly get something that's in PR, but we do not know whether these inclusions are strict or not. In fact, for historical reasons, it's traditional to denote this image here as NPR and the other one as co-NPR. And this is a better class, which is the polynomial hierarchy. This is the union of all these guys, which, well, in fact, this NP definition of NP and co-NP is not quite satisfactory because these classes are not closed under set-theoretic operations, right? Because you don't know a priori whether the complement of everything in NP is in here, but not. So might be it's better to take the union, and that relates to James' question. So this one is, if you take the union of those two, then they are closed under the standard operations. And then you can iterate these functors by taking, so pi epsilon all might be computation from 0, 1, 2, and n, and so on. So all this.
How do you go from pi sub m to pi sub m over 2 when you do the composition?
Might be I wrote it in the wrong way. So it goes from m to m over 2 and then from m over 2 to m over 4. Right? So now all this is very suggestive. So what happens if we try to replace S by CS? So we should want to have a definition of a good definition of the constructible sheaves, which are simple. Now, when you define constructible sheaves, there are two parts to it. There's the partition, which is subordinate, and the stalks, which needed to be bounded. In the complexity result, we are talking about bounding the complexity of the partition as well as bounding the complexity of the stalks when you apply. So you might not. So this is what. So this is a. Well, I'll give a formal definition in the next slide, but this is my opinion of what a simple class should be. Might be. I'm not saying that this is the best definition, but as James said in his talk, it's my talk, so I can make my own definition. So informally, and here we should be careful, that we say a class sequence of constructible sheaves on Rm is simple, is in PR, if there exists a sequence of partitions of Rm subordinate for each n, which is subordinate to Fn, but this partition is allowed to have exponentially many pieces, but you should be able to do point location efficiently. So given a point, you should be able to locate which element. And you should be able to compute the Poincare polynomial of the stalks for every x efficiently, meaning in polynomial number of steps by BSS machine. Given x in Rm, you should be able to do these in polynomial many steps.
So
now, yes. What?
What is Ti?
T raised to I. So I'm just packaging all the Betti numbers into a polynomial. So that's usually called the Poincare polynomial. That's the generating function. That's right.
Sorry.
Indeterminate, which is not of any real consequence here.
These conditions don't care about the difference. Do these conditions care about the difference between that sheaf and the constant rank 2 sheaf?
Well, the partition would be different, right? Okay, so more. And by the way, I must say that this definition is not completely. So, in work of Peter and Felipe, and also my work on previous, like Torres theorem that Maurice referred to, this kind of thing was there. So no one took the plunge to actually define complexity classes of sheaves. So that's what I'm trying to do. So more formally, we say a class of sheaves sequence is a in this simple class if there exists an index set which you might as well assume to be all integers from 1 to 2 raised to polynomial, and such that the dimensions of the stalks are bounded singly exponentially and vanish outside some polynomial dimension, and such, and these now comes the two important thing, that these two sequences of functions that goes from taking a point in Rm to the index set and computing the Poincare polynomial should be computable by BSS machines in polynomial many steps. Notice that the number of bits needed to represent the elements In, there may be exponentially many pieces, as well as the coefficients of the Poincare polynomial are bounded polynomially n by this definition. So you could possibly compute this. Okay, so there are many examples, and I have no time to go over them, but they do generalize the usual polynomial class if you take the index. Okay, so that's another example. Let's skip this. Rank stratification sheaf is another example. Let's skip that. But now we have things which are reminiscent of the BSS complexity class, that this class is stable. It needs a little bit of proof, but under all sorts of easy Sheaf-theoretic operation. It's also stable under pullbacks. But then what about the direct image functor. And here we make a definition, and this definition just follows from what I proposed before. So we look at sequences of constructible sheaves. We again have a similar adjunction, and we have these inclusions and this equality. So we now define which the class lambda R as the closure of the direct image sheaf under these easy operations. Okay. So again, we have some examples which skip, but let me just end with the main conjecture, which is that these are not equal to. So there is some relation with the classical complexity, BSS complexity, that so this one is more or less easy consequence of definition. I've snuck in a C in there, which refers to not the original BSS class, but this compact fragment of it that has been defined by me and Thierry Zell. But in fact, a stronger statement is probably true, but I put it in purple because I'm not sure that, in fact, a separation from P and PH already implies that these are not equal. So in any case, you can formulate these questions. Let me end with, I can't have time to do that, but some future directions that I think could be interesting to study.
Are there any questions for Saugata?
Can you explain again the lambda? That was very, very quick.
Yes, I'm sorry.
It's the analog of PH.
Yes, so it is the analog of both NP and co-NP.
It was somewhere on the
Yes.
very bottom of some slide. Very bottom.
Yes. Yeah. Not in this here.
Yeah.
So we have a class of simple sheaves. It's closed under taking pullbacks. These are the pullbacks and push forwards that are joined. And it's not so difficult to show that the same kind of inclusion is true. And now we want to define lambda as the image of PR under the push forward, except that we would also like to close it under operations like this, which are the easy operations under which PR is itself closed. And so might be even in the ordinary set theoretic case, one should do it because NP is not closed under taking set theoretic, a priori. And so I want to make this closed, and then we can iterate. So you project, close, iterate, project.
Any other questions?
So, constructible sheaves also have, like, once you know the stock, you're supposed to also know the generalization maps that go to nearby stocks.
This theory does not.
If I put that in, would that change the complexity?
I do not know that. That would be an interesting.
Yes. Just one question. Why did you say at the very beginning that separating, let's say, this lambda from this curve P could be easy than doing a similar separation in the...
Yes, because of this
implication.
Because of these implications. If you can do that, then it will imply this.
So this is compact.
This is compact, that's right. So, in fact, one of my open questions is to understand the notion of these properness restrictions. And the properness restrictions, in this comes in mainly because I'm using the proper base change theorems, and this requires some properness of maps restricted to the support of the sheaf. And which easy way of getting it is just to assume that. And then there is, so there are other, so since I've been talking in terms of inverse arrows which are adjoint, there are other pairs of, like the tensor home adjunctions, many other such pairs in sheaf theory, and you can ask, kind of categorical sense that you have a sequence of easy things which is preserved under one arrow, and you have an adjoint.
Maybe you can even stratify so that in each stratum the map is proper. There's also what's called flattening stratification, and you can stratify and get them. I don't know which is the notion of proper that you use.
The usual notion of properness, that the inverse image of compact would have to be compact.
The algebraic notion, there's a way of
Yeah, so
that in each.
Well, this is certainly impossible because the map from O2 to R is
Yeah.
a projection map. No stratum anywhere will this be sampled.
Yeah, this is for compact.
I mean, the free image of any point is not compact, so you're completely out of luck.
But the problem with compactness has come up before. So, for instance, the reason we introduced this compact fragment was some topological theorems relating to like the descent spectral sequence needs some kind of properness, which.
So if you ask the constructible function question, it seems to me almost obvious that you get the equivalent complexity class with functions and do it. I mean, how to say?
Yes, so my original talk had the constructible functions in the title. And maybe I should say a little bit. So you have the class of constructible sheaves on Rn. And as I mentioned, you can take the Euler-Poincare characteristic and you get a constructible functions. Now, constructible functions are very ubiquitous. Like in this semester, we have been talking about ranks of tensors and things like that, which are all constructible functions. So you might want to develop a complexity theory of constructible functions at this level, which is simpler. That's my last. And it's quite nice because if you have this direct image here, let's say pi to CS of, I don't know, R2, you have the Euler here to constructible functions on Rn over 2. So one problem with functions is that functions can be tautologically pulled back, but in the complexity questions you are interested in P versus NP of pushing forward functions. And what does it mean to take a function here and project it or push forward this function? So normally in mathematics you push forward functions by integrating along fibers, and here in order to make this suggestive diagram commute, there is only one way in which you can push forward functions, and that's the so-called, which is available for in the O minimal and semi-algebraic category, namely integrating with respect to the Euler-Poincare characteristic. So then you can develop a theory of constructible functions. You define what it means to be a sequence of constructible functions to be simple, and then you get something that is allegedly more complicated by pushing forward under taking this kind of Euler integral. And you can, to me, that corresponds to something like the VP versus VNP question in the BSS model. But unfortunately, I didn't have time. And this theory, it's developed a little bit further. There's a theory of reduction and some complete problems.
Okay, so we can probably talk further this rest of the week. We should thank Saugata again.